Welcome to week 7 of Math 320. We are more than halfway through the semester now, and this week we will wrap up the middle portion of this course. As a quick recap, after doing basic review of set theory and notations in week 0, in weeks 1 through 3 we built up the most important properties of the real numbers. For the context of doing analysis, this quintessential feature is that of order completeness. The completeness property, together with the field properties, the fact that we can add, subtract, multiply, and divide real numbers, forces on us the Archimedean property that there are no such thing as an infinitesimal. Starting week 4 through last week, we focused on studying sequences of real numbers and their convergence. The fact convergence is meaningful and fruitful to discuss owes a lot to the completeness again. Theorems like the monotone convergence theorem and the Cauchy criterion all rely heavily on the least upper bound property. This week, we will cover 2 more related concepts. The first 2 lectures, we will spend discussing a few properties of the Limsup and the Liminf. We have seen in the previous 2 weeks that the Limsup and Liminf can be used to help study the convergence properties of sequences, and that they can further be used to place limits on what are achievable as subsequential limits of a sequence. This lecture, we will discuss a different way of defining the Limsup and Liminf. This definition is equivalent to the definition using eventual upper and lower bounds that we presented earlier, but frequently having 2 different ways of thinking about the same concept can make the idea clearer, and it may help you in how you approach problems involving these concepts. This different definition, incidentally, is the one used in the course textbook. That said, much of the subsequent proofs and discussion I will still do using the eventual upper and lower bounds concept. The second lecture will concern the arithmetic properties of Limsup and Liminf. The takeaway message is, while there is something that we can say about it, the situation is much more complicated when it comes to Limsup and Liminf when compared to straight up limits. So you should be careful when you manipulate Limsups and Liminfs in a computation. The third and fourth lectures, we will take a detour to something you should all be familiar with from Calculus 2. Namely, we will revisit the concept of the infinite series. We will not dwell too much on having you implement and work with the various convergence tests, since you probably got enough of that in your calculus courses. We will focus, however, on the nuts and bolts that make the convergence tests work. In a nutshell, almost everything we can say about infinite series can be traced to the Cauchy criterion for the convergence of a sequence. So first, we need to concretely relate infinite series to sequences. This will be done in lecture 3 of this week. In lecture 4, we will use the Cauchy criterion to help us develop some of the more common series convergence tests. The focus not being on the tests themselves, which you have already seen, but on why the tests work. Starting next week, we will talk about real valued functions defined on the real line. Alright, with the long-winded introduction out of the way, let us get started. As I mentioned, the goal of this lecture is to familiarize ourselves with a different way of thinking about Limsup and Liminf. Just to set the grounds for discussion, let us first recall quickly how Limsup and Liminf were defined a few weeks ago. Throughout this short lecture, all sequences will be assumed to be bounded. The Limsup of a sequence is defined to be the infimum of all of its eventual upper bounds. Remember that a number is an eventual upper bound of a sequence if, after waiting long enough, the sequence will never get bigger than that number again. If you would like to see the precise definition, I recommend pausing the video here and pulling out the usable statements sheet for reference. Similarly, the Liminf of a sequence is defined to be the supremum of all of its eventual lower bounds. The alternative definition for the Limsup and the Liminf are captured in the formulae shown on this slide. Let's dissect the formulae a little bit. The formula for the Limsup here says that it is obtained by taking a limit. This is a limit in the index n of something. What are the terms of the sequence for which we're taking the limit? This is given by the expressions within the parentheses. So what is the term? The term is formed by taking the supremum of a set. And what set? The set is all the values achieved by the sequence with index m greater than n. So, again, start with an index n, look at all the terms of the sequence that follow it, take this set, and compute its supremum. This may or may not be a maximum. The supremum we label as the largest the sequence can get after the nth term. Now we take the limit of this quantity as n goes to infinity. The Liminf is defined very similarly. The only difference is that we take the infima of all the terms of the sequence that follow n. So we can label this as the smallest the sequence can get after the nth term. And we can take its limit to get the Liminf. It is perhaps better and easier to understand if we see a picture. In this animation, I show the process of computing the limsup and the liminf from a sequence. Like the animations of last week, here we plotted a sequence of numbers. The horizontal location corresponds to the index. Going to the right is in the direction of increasing n. The vertical location corresponds to the value of the sequence, with larger values near the top. On the far right, we plot the values of the sequence all on the same line. The sweeping purple line is the flow of time, or the increase of index. As you can see, values are slowly removed from the line on the far right. So the purple line represents the current value of n. On the far right, the values shown are the values of all terms of the sequence with index beyond the current value of n. In other words, those are the values corresponding to the dots to the right of the purple line. The values to the left of the purple line are forgotten as the current value of n slowly increases. As they are forgotten, they get removed from the set. The orange line on top represents the supremum of the set of values beyond the current value of n. The green line on the bottom represents the infima. You see that as values are removed from the set as n increases, the supremum can only get smaller and smaller, while the infima can only get bigger and bigger. The values of the supremum and infimum can stay the same for several terms in a row, if the term removed is not on the edge, so that removing it does not change the supremum and the infimum. If you remember the animation last week during the proof of the statement that every sequence has a monotone subsequence, where we discussed the notions of dominant terms, the process depicted here is closely related and very similar, but not quite the same. It is also interesting to note that this picture here illustrates why the limsup and liminf are always well defined, even when using the formula before in terms of the limit, when the limit of a sequence is in general not well defined. In the case of a general sequence, the sequence might diverge, and so the limit is not always defined. But in the formula in the previous slide, we saw the limsup and liminf defined as limits of certain sequences. So why is this a good definition? The reason is that, as we see in the illustration here, the moving supremum value that depends on n is always decreasing, since removing points from the set can only make the supremum smaller. Similarly, the moving infimum value is always increasing. As these two sequences are monotone and evidently bounded by each other, we see that the limits must exist by an application of the monotone convergence theorem. Okay, that's it for this lecture. There are no exercises for this one. See you next time.